let me just start with a reminder of what we did in relative homology. You guys remember what relative homology was?
Not perfectly. Let me just look at the notes.
What are relative chains, right? So we have a pair, A is a subset of X, we have relative chains. Right, relative chains are just chains in X up to chains in A. And then you have defined the usual way. So this is basically cycles. This consists of cycles. Well, this consists of chains that are almost cycles, right? So they consist of chains such that when you add something in A to them, you get a cycle in X. Right? So I drew this picture, like let's say X is just a square and A is an interval over here. Then this, for instance, would be a relative cycle in this picture. And if there's a hole in here, then you get an element of homology or homology. Okay, so we had the exact sequence of a pair, which was this. And then n minus 1 instead of and let me state a corollary, which is useful. I think I've stated parts of it before. First of all, what is relative homology with respect to a point? If you just pick a base point and you do relative homology with respect to that, what do we get?
It's just like the homology on the connected part that includes X0.
Can't know.
Yeah, because the
Homology doesn't have any connectedness requirement, right? It's just a sum of simplicities.
but the relative homology, like you don't have the chains don't have to be. They can also just be.
They don't have to intersect.
But
let's just ask how do we compute this? Well, the most useful, powerful computation tool is this exact sequence that we have. So if A is just a point, then we know what Hn of a point is, right? It's 0 for all positive n. So if this is 0 and the one over here is 0, then this is isomorphic to this, right? So this is basically equal to Hn of x, except for n equals 0, right?
Yeah.
Where Hn of A becomes the z. And so you have to be careful with it. But you can just think of what is H0 of x relative to a point. It's just all linear combinations of points up to this one point, x naught, which is literally taking off one copy of z off of Hn of x, which we've already defined before. That's reduced homology, right? So this is the answer. Now, if A is contractible, then Hn of x A is the same, right? This is basically just because A is homotype equivalent to a point, so it's the same answer, or same argument as here. And finally, if I've stated this before, I think if X is contractible, then we have this is 0, and the one over there is 0. So this is isomorphic to this with a shift by 1. So.
Wait, so you're using where trivial things are 0, not like integers or something?
What's that?
You're not counting. So the point isn't z. It's you're counting the 0 group.
Oh, this is z.
It is. Oh, okay.
Yeah.
You're saying 0 is confused.
Yeah,
Okay.
it kills a copy of Z.
That's also useful tool. Okay, and we kind of sort of proved the excision property which was just that you can take a pair and you can subtract the set from both sets here, and that doesn't change anything. Okay. Okay. And so with this, we have proven the two most important non-trivial properties of singular homology. First was homotopy, and excision. Okay. So now let me define a goose pair. So XA is called a good pair. Good if A is a deformation retract of an open set. So a deformation retract is right, but it's a so let's say you have some U, A is in U, U is open, and you have a function from U cross the interval into U, such that F restricted to A at all times is just identity. So points in A don't move, and also F of point comma 1 is all in A.
Okay.
And F is continuous. So that's it.
Wait, oh,
And also F, of course, at 0 is also identity. Okay. Well, by identity here, I mean identity. Okay. Okay. So let's see why this is good. Actually, all these propositions about good pairs, they also have analogs for arbitrary pairs, just more words and formulas and other things. But in differential geometry, of course, usually you only care about good pairs because A is going to be literally an open subset. So proposition for good pairs. Okay. The quotient map from XA into X over A over A. And uses isomorphisms. Okay. And also, what does this mean? So this is just X with A collapsed into a point, and A over A is just the point that A became, right? So this is homology relative to a point. So that's what we computed before. So that's the same as reduced homology of X over A. Okay. So this finally explains the connection between relative homology with respect to A and the homology of the quotient. And the first four, and not equal to 0, you can erase the total. So the proof is pretty easy. Let me draw. So let's make U the open set whose deformation retract A is And then we have this commutative diagram. Let's see what these maps are. So these are clear. So Q is the quotient by A. So that's just all it is in every situation here.
Show the quotient, right? Here you're just. So this, by that, is this that isomorphism? The excision?
Huh?
This one you're removing the set, right? You're removing a point.
Yeah.
So it's that isomorphism. The excision isomorphism. Is that
Yeah.
okay?
Well, like A doesn't exist here, right? So quotienting out by A doesn't do it. It's clearly an isomorphism. And this is by excision, the same as that thing. This is just a rewrite. Okay. And then these maps obviously change relative to A, can be included into change relative to U. Okay. Chains like this, they are just chains not in A. So they're also chains in X, like that's right. Also basically inclusion. Same here. Okay. And then you can check commutativity, basically because these are all inclusions or obvious quotients. Okay. So what I want to show is that all of these guys are isomorphisms. All of these. So 1, 2, 3, 4, 5. And then by commutativity, this has to be an isomorphism. Okay. So what you do is, first of all, H is an isomorphism by the long exact sequence of a triple. So we have the triple X U A. Right? A is a subset of U, U is a subset of X. And we had the long exact sequence, which was I guess this should be U, A, X, U, X, A. Like that. Because U is a deformation, A is a deformation retract of U, this is Altrichman. And then this is isomorphic to that. So H n of U, comma A are all 0. And H is this isomorphism, okay, from the longest sequence. Next, the same deformation retraction of U onto A gives you a deformation retraction of U over A onto A over A. Right? So this is over here. So U over A is equivalent to A over A. So I can basically replace this with A over A. So that shows that this R is an isomorphism, just the same way.
Is the quotient when open set by itself or defamation retract automatically simply connected?
No.
No, okay.
Think of a disk and a subdisk.
Okay.
Oh wait, quotient.
Yeah.
I think it is.
Yeah, because then the deformation retract can also pass down that quotient map and it becomes a retraction to a point, right?
Yeah, probably.
Yeah, I think you get a lot more for it too. Not like simply connectedness, but like also like lots of.
Oh, yeah. But once it's,
Better
once,
released.
once it's, oh, right, it's, yeah, simply connected, but.
Okay.
Yeah.
Okay, so these two are exact isomorphisms because it's the long exact sequence of the triple, and these two are isomorphisms because this is excision. Okay, and then this is an isomorphism because we discussed these are just literally the same. So these are all isomorphisms, commutes, therefore this is an isomorphism. Okay, end of proof. So we can combine this result with the long exact sequence of the pair that I wrote here before, and get the new exact sequence for good pairs. If this is a good pair, then there's an exact sequence like this in reduced homology. X. And it ends with H0 tilde X over A. Here, I is just the inclusion of A into X. So these chains get included into those chains. And then phi is the projection, the quotient map. Is the quotient map. So every chain on X produces a chain on the quotient by just killing the parts that are contained in A. Okay. Great. So this is just a combination of long exact sequence of pair. I replaced this term with this term. Okay. So let's see how this is applied. And this is yet another way of computing the homology of sphere. So we can prove that the reduced homology of an M sphere is the same as the reduced homology -1 degree of the N minus 1 sphere. Okay. And then by induction, you can compute all the homologies as usual. How do you prove? Well, you just, first let's take N greater than 0, and you take X and A. For X, you take the N disk, or N ball, and for A, you take its boundary, which is a sphere. And we know that the quotient of the ball by its boundary is the sphere, the N sphere. Right, so this is -1. So then X over A is homeomorphic to Sn. And we can just write this down. This becomes Sn. This becomes the disk, which is contractible, so this is all 0. And this becomes yes, N minus 1, right? So that gives you the isomorphism between N and N minus 1 with the shift covalence. Just what I wrote down. Yeah.
Here, why did we need that like U be an open set? If I just take any set like B over A, which includes it, then you can still create all of the maps. So So is it, does accession need some other properties from? Because in these parts, the first two isomorphisms should be included, H and R. Even if it's any other bigger set, I can include it.
Yeah, for excision, it doesn't matter, right? For H and R. Why does it matter?
So that for accession, you have no conditions, like for any set C contained in both of them, you can do that?
Yeah.
Okay. In that case, I won't.
Is it in this isomorphism?
But there you just by like triviality, right?
Good question. I don't know. It's important for something. Because otherwise,
Yeah, it should be.
good pairs wouldn't be important.
Like I feel the other way around because H and R seem like very trivial isomorphisms. So I'm thinking maybe the accession needs something.
No.
I skipped the part. I wasn't there for the accession
Yeah,
part.
excision is
So
general.
that seems like more powerful result. Okay.
Yeah, I'll have to look it up. Okay. And another couple correlated, one correlated from here is Rowler fixed point term.
We get Broward from this.
Yeah.
Okay.
So first of all, the boundary of a disk is not a retract of the disk itself, which means that there's no continuous map, from DN to DDN, which restricts to identity on the boundary. And every continuous function from DN to DN has a fixed point as a corollary of that general fact. Okay, so let's say R is a retraction. Suppose it exists. Then R composed with I is identity, where I is the inclusion of the boundary. And we have the composition of the maps and homology induced from here. We can take cycles in the boundary, include them into cycles in the end, and then retract them back into cycles on the boundary. Okay. Just maps induced by INR. And this whole composition, the composition of these two things must be identity, right? Must be identity. However, that doesn't make any sense because this equals 0 for all n. Therefore, I star is 0 and R star is 0. That composition definitely cannot be identity. So retraction doesn't exist.
Wait, sorry, I have to reprise my question.
Yeah.
You're saying that's equal to 0. You're saying it's not equal to the integers.
Hmm?
You're saying it's not equal to z. You're saying it's equal to 0.
Yeah, this is reduced homology, right? The n is contractible.
Okay. I think
The entire reduced homology is 0.
okay. I think I'm mixing it up with other things. Because I mean, like usually, like a point, for instance.
Like zero homology is 0. For reduced homology, we just throw out that z.
Oh, I see.
Yeah.
That's what I'm.
Yeah, you
That's
get
what I'm
that.
missing.
Yeah, taking one.
For sure.
A tweak to make contractible. Particularly nice looking homology.
Yeah, that makes sense.
Okay.
I mean, it should have just turned out that way, but
And then the argument for how this implies that every function has a fixed point. Are you familiar with
Yeah,
this
yeah,
standard argument?
Yeah.
When I first learned about was taught Brouwer's theorem, I think it was like, we will use the fact that there's no retraction, we will not prove it. And we will only prove this
Yeah.
part.
It's a pretty.
I technically have only seen it in an analysis class. So
Really?
it looks very, very different.
That is a weird setting to see that.
It's like,
I've seen it
analysis-
in an economics class.
Oh, that makes sense actually. Yeah.
Mhm.
I've heard that they use it a lot.
Okay, so let's say we
Nash
have a
theorem
bunch of
basically.
Let's say we have a bunch of pointed spaces, X alpha, and they take the width sum of all these, which is just disjoint union where all the base points are identified. Then we have these inclusions. And the claim is they induce isomorphisms. Just the direct sum of all I alpha stars, which is an isomorphism between the direct sum of the reduced homologies of X alphas and the reduced homology of the wedge sum. Okay. So wedge sum just turns into direct sum. This is all provided that the base points X alpha are such that the pairs X alpha are good. Okay.
So like on any manifold, this is like all those will be good automatically.
This just follows from the exact sequence of XA, where X is the disjoint union of X alphas, and A is the union of the base points.
And here you mean the base points on the disjoint union and
What's
vice
that?
versa?
Hmm?
So when you say that's a good pair, you mean on the disjoint union? Like,
No, I mean, this pair has to be a good pair for all of them.
X alpha is a point in big X alpha. And so the set containing that is
Okay.
subset. Wait, so this is interesting actually, because then, so if I'm like a real asshole and define a topology where, like I have like individual points as being open sets, like just a handful of them, then would this then give me a technique to try to say something sensible about those spaces?
Say it again.
So usually we wouldn't like to consider spaces where like single points are open. But in this case, it looks like this is giving us a tool to deal with these horrible spaces. Like at the very least, we get to say something.
I mean, hopefully not all points are open.
Right, yeah, it was just like a handful. I just throw a bunch of like jelly beans at a manifold and like say those are open.
You can refine the topology by adding it. I mean, is it that hard to deal with those spaces? I mean, provided like the set of points.
Oh, that's true. I guess it's more of a pain if you don't have all the open sets you thought you did. It's less.
I mean, I guess you can do it, but I don't think that picking those points as base points is particularly interesting because they're not connected to anything.
I see. My hope was to reduce the total number by gluing them all together, and now you have an object with maybe only like one.
Maybe,
Or two.
I don't know.
I don't know.
I mean,
Anyway.
you can try it.
I like pathological cases, and it's nice if we can analyze them.
Yeah, maybe you can do something.
Pull some borscht.
Okay. The proof of that is just the sequence A is trivial in this. And Hn of a disjoint union is obviously the direct sum of the deformations. Okay. Yet another corollary is called invariance of dimension. If you have two non-empty open sets in Rm and another one in Rn, and they are homeomorphic, then M equals N. Proof. Let's pick a point in U. Then by excision H K of U minus X. So let's excise everything but X. Okay. That's an interesting object. This is by excision the same as HK of all of Rm. And then Rm minus X. So from the long exact sequence for the pair, for this pair, we have that HK of Rm minus X is the same as HK minus 1 tilde of Rm minus X. Right. And this is a deformation, or this can be a deformation retracted onto this here, Sm minus 1. Correct? So therefore, this object that we began with, U minus X, is Z, that is Z for K equals M, and 0 otherwise, because reduced homology of SGR is concentrated in the top degree, and that's it. Right. And by the same reasoning, HK of B minus, whichever point is supposed to be the image of X, the homeomorphism, is also Z for K equals N, 0 otherwise. So a homeomorphism would induce an isomorphism between these homologies, therefore K equals N. or M equals N.
This particular corollary that required far more heavy machinery than it really deserves. It's too elementary.
I mean, but if you think about it, right, how else?
Yeah.
would you prove it? Because topologically, really, the simplest way to detect a dimension is homology, right? What other tool do you have?
Time and elbow grease.
Oh, ideal gas, measure its heat capacitance. It's proportional to dimension.
Yeah.
Like, we had this problem.
Oh.
We had this problem in first year thermodynamics. Like, advise a device that measures the dimension of spacetime.
Wait, that would put a lot of people
And
out of
basically
business.
the only
Yeah, that's right.
Huh?
That would put a lot of people out of business around here.
Only the big dimensions.
Yes.
No, yeah,
Doesn't
I mean,
change
the
the
problem
ratio.
is then the dimension is scale dependent, right?
Mm,
You go to higher energy scales and the dimension changes because you get more degrees of freedom in the ideal gas.
If you can say that with certainty, I think you have someone in Stockholm to talk to.
If you,
Okay.
This device, like if you stick it in a deep filter, you just blow it.
So this motivates this definition. It's called local homology. So X is going to be just topological space, and X a chosen point in it. Then this homology that we just saw, X relative to the complement of the point, is called local homology at X. And of course, by excision, it's equivalent to X replaced by any neighborhood, the neighborhood of X. And as we saw, it's basically, if X is a topological manifold, for instance, then this is equivalent to homology of some sphere.
Can you move your head very slightly?
It's called local homology, right? If X is a topological manifold, then this will be equivalent to homology of some sphere, and that gives you a way of detecting a dimension, homological. But in principle, it's defined for any topological space. Using this, because homology contains more information than just dimension, it also contains information like orientation, if you think about it, right? How, well, let's say Hn, suppose this is concentrated in 1 degree. So this is Z for n equals, or K, for K equals n and 0 otherwise. Then, first of all, we can say that the dimension of the space X at point X is n. That could be one of the ways to define the dimension locally in the topological space, right? I'm not saying that this is true for any topological space, but if it is, then, and also, there's a question of what is the generator of this group, right? So, choosing a generator of the Z is equivalent to an orientation. In fact, this is the topological definition of an orientation. Whereas before, to define orientations, we needed this smooth structure because we talked about Jacobians, signs of Jacobians, or even differential forms.
Screw smooth structure.
This is an orientation on the topological space.
Like, or like,
Local, so,
Yeah,
I mean,
okay.
in principle, this is only local oriented.
okay.
You can also define a bundle, beta, where the fiber over X is this group, right? So it's
Okay.
HK.
Right, and then you look at sections of that thing to get your global
Right,
order.
and so if this bundle turns out to be trivial, then that's the same as X being orientable.
Is the
And
converse-
choosing the section is the same as choosing an orientation.
Is the converse true? Like, if it's orientable, this bundle is always trivial?
If it's a topological manifold that's orientable, then yeah, of course.
Okay.
But that's just on the side base. Okay. And the final thing, kind of related to this local homology business, is called degree. On spheres, at least. So let's say we have a map F from the sphere into itself. It induces a map on the top homology. Okay? Right. But both of these guys are Z. Right. Therefore, F star of a cycle has to be equivalent to some number D times the cycle.
So this would be like winding network for,
Right. So this is called degree of F. Yeah. In physics, sometimes called winding number.
but like, this is the sort of that old, like, the first on top equals the circle for n equals 1.
So here are some properties. The degree of the identity is 1. If F is not surjective, then what is its degree?
Not surjective. Oh, yeah, 0.
Why?
Because if you remove a point, the sphere becomes contractible.
Mm.
Right. It's how much it wraps around the sphere. So.
Yes. And there's a theorem by Hopf, which says that the converse is also true.
Wait, what if you took out like 2 points?
Actually,
What do you mean? Exactly?
So like if you took out one, if F
Oh, sorry.
it's like taking
That's
out 1
not
point, then it sure looks like a disk. But if you took out 2 points, it looks like a cylinder.
Oh, yeah. But basically, like, if the image is contractible, then the degree is 0.
Yes, this is true.
Yeah. So, and you can always contract the image if you even have 1 point that you can move. That's
well,
not
the image doesn't have to be contractible itself. It has to be contained in the contractible.
Yeah. Right, yeah. Sorry. Yeah. That's
Oh,
Yeah.
I see.
Yeah.
Fine. Uh-huh.
yeah. Because then if you're going to
Because it's still a homotopy. It's still a homotopy.
if you're going to want to place it in the sphere.
If F is homotopic to G, then the degrees are the same. And so the theorem by Hopf says that the converse is true. So the degree is the only number that completely classifies homotopy classes of maps between spheres or on a sphere,
Between spheres of the same dimension.
same dimension. And number 4, degree of the composition is the product of degrees. That's just because F composed with G descended to homology. It's just the composition of the linear maps. And this is a linear property. So 5. A reflection in any coordinate plane of the standard sphere has degree -1. because reflection reverses the orientation of this. The antipodal map x goes to minus x has what degree?
-1 to the n. Because it's just n reflections
-1.
to the n, or the dimension of whatever spheres you're talking about. Or yours is a +1 because
Okay. Because it's equivalent to n+1 reflections if you wish. Because it's Rn plus 1. The sphere in Rn plus 1. And then 7, if f has no fixed points, then the degree of f equals what?
f has no fixed points, then its degree is 0. Is that, wait,
That's not very fixed points.
no, that's not.
Give me an
Wait.
example of a map that has no fixed
No.
points.
No, I don't think I.
Sphere rotated a bit. Or sorry,
No,
circle rotated.
No. It's only this map only exists if it's a circle, right? Or maybe it's an odd dimension thing, one or the other. But I know that this doesn't exist for S2.
It does.
It does? What? Hmm. Oh wait, the antipodal map. I guess.
Yes.
Fine. Fine.
So that's
Yeah.
sure. But
Wait.
it's still a theorem that needs proving.
Yeah.
Oh,
There's stuff
okay.
like that.
So it's automatically, wait, not, no, sorry. That's in odd dimensions.
Because then one has to check like, oh, you do the antipodal thing and then you rotate it a bit.
So in odd dimensions, then every,
So that's kind of the
every map of the
only,
sphere to itself.
the
has
antipodal
a
map is
fixed-
the
or
only
even
non-fixed
dimen-
point map.
even dimensional
up to
sphere.
model.
Every map from the identity from the sphere to
Um,
itself.
Yeah, so the proof of
On
this,
topic to the identity has a fixed
you
point.
take this function and you literally construct the homotopy
Between-
to the antipodal map. Okay.
And so, all right.
Mm. Another definition is called local degree. So we can take any map between, let's say, topological manifolds, and topological manifolds, and we can take F star on local homology. Into n. Okay. And this has to be a multiplication by a number, which is called degree f. But degree at this focal point is degree of x. Okay.
Wait, so is this like particularly boring for smooth maps, or can you have smooth maps that do interesting things here?
What do you mean? These are maps that have a winding, right? It's like, think of a polynomial, for example, in the complex plane. A zero of a polynomial has a non-zero degree, has a non-trivial, so not equal to 1 degree around the
Okay.
zero.
But everywhere, but that's not the
Here,
case for any non-zero point, right?
Yeah, for any non-zero point, it's going to be degree 1, degree equals 1.
Okay, so like these will be typically identified special points essentially?
Yeah.
Or critical points of some sort?
So you'll be assuming that the nth homology is Z. Like if it's
Yeah, I said
Z.
these are topological manifolds, so it's either Z. And they're both n-dimensional. Okay. Okay, so a proposition which I'm not going to prove because I'm lazy is that if you have any map between two spheres and y is a point such that the pre-image is finite, and finite, then the degree of f equals the sum of the local degrees of these points as a generic range. Okay. So corollary, fundamental theorem of algebra. You know, that states, so.
This is my favorite proof.
Ta-da.
You make it interesting and use this to do it in nocturnials, which apparently you can't. Or you can do it with your own. I don't know if you can do it with also that analysis.
Interesting.
Okay, so let's say we have a polynomial of non-zero degrees.
Associativity, I'm going.
It's just there lots of. Sorry.
We have a polynomial of non-zero degree, and we want to show that it has 0. We can think of it as a map from S2 to S2, where there's a fixed point, right? Even if it's infinity, because it has non-zero degree. The critical points are exactly the points where p prime is 0, because for a holomorphic function, 0 Jacobian is the same as the complex derivative being 0. And there are finitely many critical points, because p prime itself is a polynomial, and any polynomial definitely has only a finite number of zeros. Because it's infinity at infinity, therefore all of its zeros must be contained in a compact subset of the complex plane. And if there were infinitely many of those, they would have to have a converging subsequence, which would make the whole polynomial 0 by properties of holomorphic functions. Okay, so definitely finitely many. And therefore, there are finitely many points that are not regular values. They're not regular values. Because there's only finite critical points, therefore finitely many critical values. Now, the image of P is connected because it's a continuous function. And P is not constant. Therefore, there exists a regular value in the image of P, because the image is infinite, right? And there are only finitely many non-regular values. So, however, Jacobian of P is always strictly positive because the holomorphic function, right? Preserves orientation. Well, I should say, positive at regular points. Therefore, local degree at a point that gets mapped into a regular value is +1, right? So it could be either +1 or -1. But because the Jacobian of a holomorphic function is always positive, it's always +1. But therefore, by that proposition, the degree of P is strictly positive. But if the degree is strictly positive, then it's not 0. Therefore, the image of P has to be the whole sphere. Because if it's not the whole sphere, we know the degree has to be 0. Therefore, 0 is contained in the image of P.
Fancy.
Yeah. That's it. homology. Now we will examine the first homology and understand its relationship with the fundamental group. Okay. So this is called Gurevich theorem. That's how it's pronounced.
Is that Polish? Polish.
Yeah.
Gurevich.
It's not Horowitz, it's Gurevich. W is a V and CZ is always a Chisholm. Okay. Okay. So, so H0 we've already understood, right? Because it's just a free abelian group generated by the connected components of X, which is the same as pi 0 of X, basically by definition. But now H1 of X, how is that related to pi 1 of X? That's the question. And we already know that they're definitely not the same because pi 1 is not abelian, and H1 is abelian. What's the next best approximation?
The abelianization of pi 1?
Yeah, so maybe that tilde means factor by commutator subgroup. That's Gurevich theorem. So first of all, for any two paths such that the end of the first path is the beginning of the second path, we can multiply them, right? This is a multiplied path. So we will use this fact. And this is still going to be defined on the other one. So you concatenate them and then speed up by a factor of 2. So first lemma, if you have two paths in X and gamma 1 of 1 equals gamma 2 of 0, then the one chain gamma 1, gamma 2 minus gamma 1 minus gamma 2 is actually boundary. It's a boundary. Okay. So we did this, and then subtract. Yeah. Compose, and then subtract. So it's a degenerate triangle, basically. And this is basically the main part of the whole theorem. The proof is pretty simple. So we define a piecewise map on the standard 2 simplex. So let me draw E0, 1, E2. We have the 2 simplex. Let's define the piecewise map on it by putting gamma 2 on this edge. Gamma 1, gamma 2. Okay. And then, so this doesn't define a map on the whole simplex, just on the 2 boundaries. Okay. And then we define a singular simplex from this. Recall, a singular simplex is just any map from this simplex into X. So I want to define a singular simplex by saying that sigma is constant on lines perpendicular to E0. Okay. So what happens is it's constant on these lines. right? So it's gamma 1, gamma 2, and the image here ends up being the composition of gamma 1 and gamma 2, right? And everything in between also gets mapped into the same points by this rule. And then obviously gamma 1, gamma 2 is on the edge of along this edge, and the boundary of this is gamma 1, 2 minus gamma 1, gamma 2 plus gamma. Did I mix up the signs? Should be wait minus that's right. Yeah. Okay. So it's a boundary. Okay, what does this mean? So this means that in homology, gamma 1, gamma 2 is the same as that, okay? But this operation here is abelian, right? Because it's an addition. This operation was not abelian in homotopy. So what this is saying is that multiplication of paths, which was non-abelian homotopy, now became abelian in homology, right? And that's basically the main reason why the only difference is that you just abelianize. Okay, so another lemma, just a corollary of that basically. If gamma is a path, then gamma plus gamma inverse is a boundary. And also the constant path is a boundary. First, you prove that the constant path is a boundary. It's like obviously the boundary of the constant simplex. Okay. So constant path is a boundary, and therefore this in homology will be equal to gamma times gamma inverse, which is equivalent to a point, a constant path, which is a boundary. Okay. What does this imply? Well, I guess before we figure that out, one more lemma is that if gamma 1 and gamma 2 are homotopic relative to the boundary of the interval, which means, I should have introduced this terminology before, but relative to the boundary just means that the endpoints are fixed. Okay, so on the boundary on the interval of the interval 0 and 1, the values of gamma 1 and gamma 2 must be fixed and equal. Then they're homologous. They represent the same class of homology. The proof, again, is simple, because F is a homotopy between paths, which means that it's a map from the square into X, right? Such that on two sides of the square, there's gamma 1, gamma 2. But all of this gets mapped into gamma 1 and 0, and all of that gets mapped into gamma 1 and 1, right? So basically what you can do, I'm not going to write out the formulas, but you can contract, you can just produce a map on a triangle out of this, right?
Yeah. Contract the square.
Just contract this, and this produces a map like that. That's a singular simplex in X, whose boundary, this is just a point, so that doesn't do anything. So its boundary is basically gamma 1 minus gamma 2, which is 0 in homology, because it's a boundary. So therefore they're homologous. This is very simple. And we are ready to define the homomorphism from homotopy into abelianized homotopy into homology. So theorem Hurwitz. So phi 1 of x comma x naught is going to be the abelianized homotopy, fundamental group. And x is, let's say, dot connected, so that we don't lose their components. By the last lemma, we have a homomorphism called phi from phi 1 into H1. Right. So we take paths, abelianize, that's a homomorphism because homotopic paths are homologous. Right. So this is actually a well-defined homomorphism from phi 1 into H1. The statement is phi is an isomer. Okay. What do you do? To prove this, let's say we have some path gamma. Let's define gamma hat as, first of all, for any point P, let's define gamma P as just some fixed path from x naught to P. Just choose a bunch of paths from x naught to every point in x.
Yeah.
And assume that gamma x naught is just a constant path. And then define gamma hat for any path as gamma to the beginning, then gamma, and then gamma from the end back to x naught. This is a loop based at x naught. And let's define psi, which is the thing that's supposed to be inverse defined, as just the homotopy class of gamma hat in in phi 1 is a little bit confusing because there are equivalence classes on both sides. So I'm going to be writing explicitly what I mean, which equivalence class I mean. Okay. So this extends, psi extends to a homomorphism because phi 1 tilde is an abelian group, right? So it's enough to define on generators of chains on loops, right? Which are, sorry, not on loops, on one simplex, right? Because a path is just a one simplex, a singular one simplex. So this extends to a homomorphism from C1 into so we need to show that psi takes boundaries into 0. And therefore it descends to a homomorphism on homology. So H1. And then we can check that psi composed with phi is identity in projections. Okay. How do we show this? Let's say sigma is a true simplex. You can just check by direct computation that psi of the boundary of a two simplex is represented by a constant man. Basically because
You just contract along the interior of the simplex.
yeah, basically because you have these three paths going around and the triangle is contracted. So, okay. So therefore, so this proves that psi on boundaries is 0, and it remains to show that psi composed with phi gives you identity in both directions. First of all, psi star phi star is identity because for a loop gamma, we have psi star phi star gamma is just gamma x naught, gamma x naught inverse, but these are constant paths. And this operation is commutative, remember? So this equivalence class is taken in H. So this operation is commutative now. So this cancels this, and this is the class of gamma. Okay. So this composition is identity. In the opposite direction, phi star, psi star of one simplex is going to be gamma sigma of 0, sigma gamma sigma of 1 inverse. But again, multiplication gets converted into sum or subtraction. So this ends up being sigma plus gamma sigma of 0 minus gamma sigma of 1 by the previous lemmas. So if you have C, which is a one chain, then phi star, psi star of C is just, C is just a linear combination of one simplices like this. So the image of C is going to be the sum of the simplices in it, so C itself, and then plus a bunch of paths going into the endpoints of C. Right. So if C is something like, I don't know, like that, right? Then the image of C is going to be C, and then plus these paths, respecting the orientation. So depending on the orientation of these guys, this will be in either one or the other direction, or the sign in front of it. So what this ends up being is just C minus gamma dC. So this is just my notation for the sum of these paths here. But obviously, if C is a cycle, then dC is 0, and this is just C itself. So therefore, on cycles and on homology, this is identity. And that proves the theorem. Okay. Any questions? So now the natural question, of course, is what about higher homology?
The question which one may be afraid to ask.
Right. So first of all, higher homotopy groups are abelian. So you might hope that they are just the same. In reality, you can construct a similar homomorphism from phi n, and this time you don't need to abelianize anything right into Hn for n at least 2 by just phi n is a map from the SPRSN into X. That's basically an n chain because you can triangulate the sphere, and then homotopies here, or homotopic maps of spheres into X, are also homologous, right? The images are going to be homologous because homotopy sweeps out the space whose boundary is what you need to prove that they're homologous. Okay. So yeah, so this is, you can check that this is a homomorphism. And the Krivich theorem for higher groups is this. If X is path connected, but also n minus 1 connected, which means that, and n is at least 2, which means that all homotopy groups up to n minus 1 are trivial. So I k of x trivial for k from 0 to n minus 1. No, sorry, 1. 0 would be z because it's path connected. Then hk of x is 0 for all k less than n.
Isn't pi 1 0 because it's path connected, or pi 1 trivial because it's path connected? Or sorry, pi 0 trivial because it's path connected?
No, it's z because it's path connected.
But
Pi 0 counts the number of components.
But path connected spaces have one component, right?
Yeah, so
Yeah,
z.
so it's one.
Oh,
Yeah.
sorry. Wait.
Right, yeah. Okay, so if pi k's are trivial, but they have to be, not just one of them is trivial, but all of them must be trivial from 1 to n minus 1, then the corresponding homologies are also 0. And on top of that, hn from pi n x naught into hn x is a nice marker. Right. So if it's n minus 1 connected, then the nth homology and homotopy groups are the same. But then anything higher from there, you don't know. So it's a pretty weird statement. But it's still very important in topology. I'm not going to prove it. Okay. So there are things, because of this, basically, there are things like Eilenberg MacLane spaces. Have you heard of those?
I've heard them. I don't know if they are the.
Yeah. So those are spaces basically with,
Oh, those are classifying spaces. Is that the same?
they're related, but they're basically spaces with prescribed homotopy groups. So basically, say you take any group you want at all, and you say, I want to find a space such that it's G for k equals n, and it's trivial or 0 for everything else.
So it's like a generalization of classifying spaces.
Wait,
Where
so G
this
needs
is
to be
called-
abelian here? If there's not one?
Yeah.
K of ng or gn, something like that.
Classifying spaces are just when k equals 1, right? Or, yeah. K
These are not literally spaces, these are weak homotopy equivalents classes of spaces. But so in homotopy theory, they are well-defined objects.
You can show for any group you throw at this.
Yeah.
there's a-
And you can always realize them as CW complexes. Infinite dimensional, but CW complexes.
Wait, but they're, the claim is that there always exists an X.
For and n, like
Yeah,
isn't
and this
it?
X can be, there's a constructed,
Mhm.
an implicit construction of what this X must be.
So all abelian groups n ends up being one.
What this
sorry,
X could
all
be.
non-abelian groups n ends up being one.
Huh?
Or for not all non-abelian groups, n has to be one.
Oh, well, yeah, G, again.
Oh, okay. Sorry.
Are you leading us?
I have another reading group that I started.
Huh?
There's another reading group I started going to. So
What is it about?
that's for a specific proof of a conjecture, called the 2-to-2 conjecture.
What conjecture?
The 2-to-2 conjecture. It's computer science. It was just solved recently. It's like a breakthrough result. It's proving that.
Okay, so we have just a little bit to finish up general singular homology stuff. First of all, let's finish the debate of singular versus simplicial homology and establish that they are the same for triangulable spaces or simplicial complexes. First of all, we can define, so let's say X is a triangulated, and A is a subcomplex. So it's the union of simplicities in X is a simplicial complex. Then we can define, as usual, relative chains, simplicial chains in X as just, relative to A as just simplicial chains in X over simplicial chains in A. And then you have Hn A as usual. We want to say that we want to prove that this is the same as just singular homology, which is going to be Hn without the triangle. Okay, how do we prove? And specifically, the map from simplicial to singular is obviously just the inclusion rate.
I will also be leaving to go to the KPTC office and pick up homework sets, some of them before the weekend.
Will you be back?
How much longer are you going?
Like half an hour.
Like half an hour. Yeah, I want to get there before 4, so we'll be back.
But this uses 5 lemma. This is the place where we use the 5 lemma. It's so cool.
I will wait for the statement of the theorem.
The proof is, the statement of the theorem is simple, but you should see the proof. It's like 5 minutes. Okay. So
5 minutes.
So these homomorphisms, Hn of X A, are isomorphisms for all n and all pairs of simplicial complexes. XA. Proof is based on this very cool diagram. Let's denote by xk the k skeleton of X. Right, so that's the union of all k and lower simplicities of X. And let's assume for the beginning that X is finite dimensional and A is empty. If A is not empty, it's just literally all the same with comma A added everywhere. Then we have this diagram. Okay. And down here, it's all the same without the triangles. Do you recognize these sequences? The rows.
So these are subsets.
What are these sequences?
So is there
The
This is-
relative ones,
Ah,
XA, XA.
Yeah, this is the
XA.
long exact sequence of a pair.
Yeah.
A, X, X comma A, etc. So these are just a segment of length 5 of that sequence. And then these are the homomorphisms that we need to prove are isomorphisms, right? Specifically, these between the X's. Okay. What we can prove right now is that first of all, we will show that the first and the fourth maps are isomorphisms, so between these relative homologies. Why is that? Well, that's because these homologies are very simple, right? It's just k skeleton relative to x k minus 1 skeleton. What are these relative chain groups.
They're just a bunch of spheres glued together.
Right. So basically, this is, but this contains only k simplices, right? So this is 0 if k is not in, or if n is not equal to k. So 0 if n is not equal to k, and this is a free group if n equals k, free generated by all k simplices in here, right? So therefore, hn of this is equal to cn of that, right? Because everything else is 0. There are no kernels to factor in. Okay, so these hns are very simple. And the singular homology over here on this side can be computed by considering the map phi between the disjoint union of delta alpha k, the boundary of alpha k. Remember how simple shell complex was constructed? We just take a bunch of standard simplices and glue them along the boundaries somehow. And you get the, in this case, you get the skeleton relative to the boundary, or to the k-1 skeleton. So this phi is just formed by the actual embedding maps of these simplices into X, the triangulation of X. And this phi is a homeomorphism on the quotient spaces, right? When I quotient this union by that union, that's supposed to be exactly Sk with that. So phi is a homeomorphism on the quotients, induces a homeomorphism on the union by the union boundaries, isomorphic to xk by xk-1. And therefore it induces an isomorphism on homology groups of these two things. Right. But the homology group of this is 0 when n is not equal to k. And for n equals k, again, it's a free abelian group that's generated by a basis represented by the relative cycles given by the embeddings of these k simplices, basically. That's because hk of delta k d delta k. What is this? Well, this is just the k ball, k disk, basically, relative to the boundary of the k disk. That's a sphere, k sphere. K of the k sphere is z, and generated by the identity map, delta k and delta k. Right, so this is z for each simplex. So this is indeed a free abelian group generated by literally these simplices, the identity maps on them, or the embeddings of them into those. Okay, so that establishes pretty much that this group is isomorphic to this one, and this one to this one. And now the beautiful part. What we want to show is that this is an isomorphism. Okay, look at this. This is n and k. What about these two things? These two things. This has n-1 and k-1 and k-1 here. So what we can do is induction in k, right? So let's assume that k-1, these are already isomorphisms, and these are isomorphisms, and this are isomorphisms. By phi lemma, this is an isomorphism. And the theorem is done. And the base is also trivial. But because for points, singular homology is the same as singular homology.
Can you,
And then, yeah.
can you extend the chain backwards into zeros?
Right,
H minus 1.
Hmm?
You can formally define H minus 1 as 0. Does that break anything?
Why would they break anything?
A little bit back. But then your inductive assumption, it seems like, would become quite straightforward there.
count. I don't know if these sequences don't really they go to zero, they stop at zero.
Oh, but if you continue them into zeros, like into trivial groups, does that break the exactness of them?
Maybe not.
No.
I mean, if you just add infinity of zeros on there, it doesn't break anything.
Okay, because it just seems like that induction order.
And then there's a simple argument that if X is infinite dimensional, then singular simplices are maps from compact sets into X. And the image of a compact set can overlap only finitely many simplices. So basically, you can restrict the whole argument only to finite dimensionals of complexes of X. And it takes a little bit of work. But, it works. Do we want Kyle to be back?
I think I might call it a day too.
Okay.
Yeah. I sadly have a plethora of distractions as you're probably aware.
Okay. Mhm.